Hi, and welcome to our next Level 2 Calculus video. In this video, we're going to talk optimization problems. And this is the part I love to teach in class because I think after years and years of doing algebra, it is the first time many students actually realize how it's used in the real world and how important this is. Calculus is used to determine a maximum or minimum turning point. Hence, this idea can be used to determine maximum and minimums in many applications, such as we might want to be maximizing or minimizing area or volume. We might want to maximize costs or profits. We might want to minimize things like surface area because we might be building a new type of can for a liquid and we want to have the least amount of surface area on our can. Or we want to minimize things like waste or staff or time. All right, optimization problems. Most of them are going to follow a similar format to what we're going to show in this video. So let's go through the steps. Step 1, determine the function that needs to be maximized or minimized. Use another rule to make sure the function only has one variable. We don't always have to do that, but sometimes it's useful if the function we need to maximize or minimize has two or more variables. Differentiate the function to find the gradient function. Put the gradient function equal to 0 to find the maximum or minimum. And finally, use this maximum and minimum to answer the question. Right, let's go. One example, let's show you these steps in action. A farmer's got 120 metres of fencing to build a rectangular paddock. One side of the paddock is a stream and does not require fencing. Determine the dimensions of the paddock and calculate the maximum area possible. Right, I love diagrams, so here's my diagram. The blue line is my stream, and I've got three sides of my fence. So I'm going to call my bottom base X and my two vertical sides Y. Right, the area of the rectangle, is base times height, which is X times Y. That's the function we want to maximize. But it's got two variables, X and Y. So this is what we're going to do to solve that. We're going to use the perimeter of the fence. X plus Y is 120. So that simplifies down to X plus 2Y is 120. We can subtract X off both sides and get 2Y is equal to 120 minus X. And we can divide both sides by 2 to get Y is equal to 60 minus half of X. Now we're going to grab this function Y equal to 60 minus 0.5X and we're going to substitute it back into the area rule and replace the Y back here. So we're going to write down area is equal to X times, instead of Y, 60 minus 0.5X, because that is equal to Y. And, oh, hang on a second, I'm sick of writing area, so I'm just going to be cheeky and write A for area instead. And now we're going to say A is equal to 60x minus 0.5x squared. I've expanded out the brackets. Right, well, this is a function that works out the area of the paddock, and it's only got one variable, which is X. So let's move on and do some calculus. Let's differentiate the area and work out A dash, or the formal way of saying it is dA over dx. And that's 60 minus x, because 60x differentiates to 60, and the 2 comes out the front and times is by the negative 0.5 to get negative 1, and then we drop the x squared down to a power of 1. So this is the gradient rule. So let's put the gradient equal to 0, because a turning point occurs when the gradient is 0. And let's solve that to get x is 60. So we've just figured out the base of this paddock has to be 60. So going back to here, we see y is 60 minus 0.5x. Let's substitute x is 60 into this rule to work out y has to be 30, and we get our y values of 30. Checking they all add up to 120, which they do, we can now work out the area of the rectangle, which is 1,800 meters squared. That is a maximum possible area. Now go and practice this, because this is one example and optimization has many examples. Thanks for watching.